Alright, so final topic that I wanted to cover in this Calc 3 review is surface integrals, where I think this will be some new stuff for you guys, but it'll also be what you guys will start covering soon. So I think that this is important. So the idea of a surface integral is just like before. We have some function f where it's a vector, but in this case we have some surface and we want to know, as we integrate up over this surface, how much f is coming out of it. And this is sometimes written like as the flux. So you will sometimes see something that looks like this. Where I should actually draw two integral symbols because it's going to be a two-dimensional integral. So let's break down this equation. So just like before, we have the function that we're interested in integrating. We have this n hat, where the n hat is a normal vector. And what this tells us is to increase our flux, we want our function to be parallel to our normal vector. So what does that mean? Well, let's think about this whiteboard, and let's think about our vector function as like a stream of water going through. And we want as much water as possible to go through the whiteboard. Now if we have our water and it's going up like this, most of it's going to miss the whiteboard. We're not going to get a ton right through it. On the other hand, if we have our water coming straight in, where it hits the whiteboard, we're going to have a ton of flux through the whiteboard. Just keeps going through it. So in this case, with the whiteboard, our normal vector will always be pointed like this. And so if you get a flow where it's almost perpendicular to that, you're not going to get any flux through the whiteboard. But if you get a flow that's parallel to that, you get a ton of flux through the whiteboard. Then comes this dA and the integral symbol, and what that just means is you have to integrate up over the entire whiteboard. Where this can get kind of complicated, like if you have a weird surface, and especially if your flux is changing over the surface. What's usually good is if you have it where your function just stays constant within an area. Like let's go back to the stream of water analogy, where we have a constant velocity of water just going through in an area. Let's say we just have vector field is just like this. We have our surface. It's just a flat surface with our normal vector like this. And there's a very easy way for us to calculate flux without having to do a difficult integral. We can just go flux is equal to F. I'm going to leave off the vector sign. It'll just be the magnitude of F times the area. Obviously, the bigger area you have, the more stuff that can flow through it, times cosine of theta, where theta is the angle between the F and the normal vector. So it can be a bit confusing because this means that F would be, for cosine to be 1, for that theta to be 0. Let me stop, that might be confusing. When theta is 0, that means that F and N are pointed in the same direction, and that means that F is completely perpendicular to the surface. And anyway, this is a pretty useful tool that you can use when calculating the different fluxes. Alright, so I hope with some of these videos, some of the older lectures that you're getting, that things will make more sense. If not, feel free to contact me and ask any questions that you want.